Now I'm going to do the same thing again for LightGBM. So LightGBM is Light Gradient Boosting Machine. So that's Microsoft's take on the gradient boosting um, algorithm. And basically, again, I'm gonna use these particular hyperparameters and estimators, the max depth, learning rate. These are sort of the basic ones, the bin, the subsample, and the number of leaves. And so there is a lambda 1 and lambda 2 for L1 and L2 regularization, but I found that just no matter, even though I'm supposed to find optimal values, I found that like um, not having them gives me better results. So basically, I'm either just totally off in what the range I'm choosing for them, so I'm continually just choosing suboptimal levels, or something else is going on. So anyway, these are the important ones for me. And again, the estimators has to be an integer, the depth is an integer, the number of leaves is an integer, and the max number of data samples you have in a bin must also be an integer. And again, I'm using cross-validation using RSKF. So again, that's what, 5 splits and two trials. Scoring again is Matthews, and I want to see what values of these things give me the best mean cross-validated score. So the ranges of these particular hyperparameters are kind of similar to cap boost, though I might have changed them a little bit. Um, Estimators 50 to 200. This my learning rate very rarely goes above zero point 0.4 or zero point 0.5. Subsample is still zero point 0.5 to 1. Number of leaves is 15 to 50. So this is kind of the same. And again, I'm just running this. This function is called LGBM opt, right? And then I'm trying to optimize using this function. I'm optimizing this function here, the LGBM dot underscore opt, using these parameters, these p-bounds. Verbose means that you see everything. And then again, 2 initial points and 20 iterations. So let's run this and see how this one is faster. So you can see it's already off to a good start. 93.75 is the best so far. And you want to take note of like what the ranges of these hyperparameters are. So obviously pay attention to the ones that are good, but also the ones that are close. So you can see learning rate 0.48. So maybe that suggests that like my learning rate should always be like kind of higher than zero point 0.1. I mean, if you look over here, you'll see like 0.45 gives me 93, but like this 90.27 here is at a 0.28. So basically, I could try to narrow my learning rate down to something like zero point 0.3 to zero point 0.5 or zero point 0.4 to zero point 0.5. Max spin 100. The depth is 6, so higher depths than normal, kind of the normal 2 or 3. And estimators didn't really need that many. The number of leaves is pretty low, and subsample. So basically, this is preventing some overfitting. And now I'm going to basically do the same thing here, which is to take all of these and then convert the ones that aren't in integers into integers. So now you see max spin's 101, the depth is now 6, estimated is 54, so I have integer values. And basically I'm going to take these best params and then I'm going to, here I didn't save it as something else, but I'll take the best params and remember the 2 asterisks are how you put a dictionary of hyperparameters into this as an argument. So I basically am training the LGBM with these parameters. I'm fitting it on the entire data set, and I'm looking at the cross-validated scores of this regressor over x1 and y1 with this cross-validation scheme, right? And with the Matthews correlation as my scoring mechanism. Again, I'm looking for the mean of the scores, and then I'm going to do confusion matrix on the whole thing. So if I run this, you can see here that the Matthews score is 0.93, which is not, which is, I'm not sure, maybe close to what the cap boosts was. But you can see here that when you train it on the entire data set, you end up with the same confusion matrix. So 197, 320, 0, and 3, which is confusing because then, you know, you feel like Well, it's not confusing because it's the math used is based on the confusion matrix, but not of this global one for x1, y1, but of each fold. So, but in the end, if you think about it, if you sort of consider the entire data set like the end goal, then it comes out pretty much the same. And if you look at the SHAP values, then you'll see here with LGBM, it comes out in two colors, as it does with random forest. Basically, it's still, you can sort of ignore this part. I mean, the idea is basically that higher values in the red here usually lead to higher values of, well, it leads to higher, as in closer to 1. So higher values of polyuria usually will push you to higher values. So it'll push you closer to being positive. So here you have polyuria, polydipsia, again, as the most important features. But then you have gender, itching, prophylaxia, age, weakness. So weakness was one of the weaker ones before. Obesity is still kind of at the bottom, though. But gender, itching, polyphagia are important now. But how did they figure in the other one? So if I go back up to my other one here, I see gender is, so it sort of agrees in the first sort of three-ish. Polyphagia is still up here, but it's not quite as high. So you can see that in these particular models, random forest and the LGBM, that sorry LGBM and cap boost, that they are sort of consider the features a little bit differently.